On March 23, 1989, two chemists stunned the world when they announced that they had achieved cold fusion in a laboratory. Martin Fleischmann, one of Britain's leading electrochemists, and his colleague Stanley Pons, then chairman of the University of Utah's chemistry department, reported that they were able to create a nuclear reaction at room temperature in a test tube. Since then, cold fusion has been replicated in hundreds of experiments in dozens of major laboratories, all reporting similar results under similar conditions. But what is cold fusion, and how do we know it is real? Cold fusion is a nuclear reaction that generates heat without burning chemical fuel. Cold fusion has reached temperatures and power density roughly as high as the core of a nuclear fission power reactor. Unlike most other nuclear reactions, it does not produce dangerous penetrating radiation because it consumes hydrogen in a nuclear process rather than a chemical process. The hydrogen generates millions of times more energy than the best chemical fuels such as gasoline and paraffin. Hydrogen fuel is virtually free, and cold fusion devices are small, relatively simple and inexpensive. They are self-contained, about the size, shape, and cost of a NiCad battery. They are nothing like gigantic nuclear power reactors, so the cost of the energy with cold fusion would be low. If researchers can learn to control cold fusion and make it occur on demand, it might become a practical source of energy, providing inexhaustible energy for billions of years. It would also eliminate the threat of global warming because it does not produce carbon dioxide. Most cold fusion reactors produce low heat, less than a watt, but a few have been much hotter. Here are 124 tests from various laboratories, grouped from high power to low. Only a few produced high power. Most produce less than 20 watts. In 1996, at Toyota's IMRA research lab in Europe, a series of reactors produced 30 to 100 watts, which was easy to detect. They continued to produce heat for weeks, far longer than any chemical device could. The core of the Toyota reactor was about the size of a birthday cake candle. A candle burning at 100 watts uses up all of the fuel in 7 minutes, whereas one of the Toyota devices ran at 100 watts continuously for 30 days. That's thousands of times longer than the candle. It produced thousands of times more energy than the best chemical fuel. So, if the tests were so promising and were able to achieve such high power density and run so long, why hasn't cold fusion become a practical source of energy? Because cold fusion reactions can only be replicated under rare conditions that are difficult to achieve, even for experts. It's like making a soufflé. If you forget to put the egg whites in the soufflé, even if you set the right temperature and do everything else correctly, you get no soufflé. But when the right conditions are achieved, the reaction always turns on. SRI International and the Italian Agency for New Technology were able to get all of the critical factors just right and achieve the cold fusion reaction in several tests. It is not difficult for an expert to reach a ratio of hydrogen atoms to palladium atoms of about 60%. This takes a few days, but it isn't high enough to trigger a cold fusion effect. You have to go higher, and the higher you go, the harder it gets. But with the right kind of metal and good techniques, the amount of hydrogen in the metal gradually rises. When it reaches 90 atoms and other conditions are met, bingo, the cold fusion reaction turns on. This graph shows an exponential increase in power when the ratio of hydrogen atoms to palladium atoms exceeded 90%. A Toyota lab also saw the exponential increase above 90%. Hundreds of other researchers have seen the same effect. Another factor that makes the cold fusion effect turn on is electrical current density. The higher it gets, the more intense the cold fusion reaction becomes. When there is a reaction, that is. If there is no reaction in the first place because, for example, the ratio of hydrogen to palladium doesn't get above 90%, raising the current does no good. We've learned a lot since the Fleischmann and Pons announcement in 1989, and we know what now must be done. But knowing how to do something doesn't make it easy. We have to learn more. With enough research, scientists may learn to control cold fusion and make it safe, reliable, and cost-effective. But it's going to take thousands of hours of research and millions of dollars of high-precision equipment. Basic research is expensive. However, if this pans out, it will reduce the cost of energy worldwide to practically zero, saving several $billion per day. This might happen as quickly as microcomputers replaced mainframe computers, or the speed at which the Internet expanded after 1990. It can happen quickly because it requires no distribution infrastructure, and it calls for only a few changes to most core technology. In other words, a cold fusion-powered car would not need a gas station because you could run it for a year with a spoonful of fuel, costing a few cents. But that is information for another video, another day. To learn more about the potentially groundbreaking research surrounding cold fusion, please visit lenr.org. Thank you.